Okay, last chapter, chapter 22. So I have here sections that I'm completely skipping. This isn't a lot of pages out of the whole chapter. So I'm going to be covering most of the chapter, but I'm not going to go in as much detail in many areas as what the book does. So basically, if you understand this at the detail that I presented in this lecture, then you should be good. You don't need to know it super deep as much as the book has. Okay. So this chapter is on mixtures, and most foods are a mixture. I think we've talked about this somewhat. Uh, there there's some kind of mixture, and there's different types of mixtures that we'll talk about. Within a mixture, there are always two phases. Okay, no matter what type of mixture it is, there is a dispersed phase, and these are the particles that are scattered throughout the medium. Okay, so this is in the red in this image is the dispersed phase. And then there is the continuous phase, and that is the medium in which the particles are distributed. Okay, so uh, that is what those particles are in. Okay. So the three types of mixtures. So all mixtures have these two phases. And then there are three types of mixtures, and how this dispersed phase and continuous phase are in those mixtures determines what type of mixture it is. Okay, so solutions have extremely small particles in dispersed phase. We are talking about compound level atoms, compounds level particles that are in the dispersed phase. Okay. Then when those particles become a little bit larger, they are not just small chemical compounds, but they're things like proteins and like bigger compounds. Uh, then they are colloidal dispersions. Okay, so the smallest dispersed phase is the solutions. When the particles in the dispersed phase become a little bit larger, they are colloidal dispersions. And then when you have much larger particles in the dispersed phase, these are suspensions. So typically in suspensions, you can actually see the particles with the naked eye. With colloidal dispersions, you're going to be able to see them only with a microscope, maybe. And then solutions, you're not going to be able to see it with a microscope even. So more about solutions. Solutions are going to be a homogeneous mixture of two or more substances. And the dispersed and the continuous phase have special names when we are talking about solutions. In solutions, the dispersed phase is the solute, and the continuous phase is the solvent, right? So the solvent is what is dissolved. The solvent is what the solute is dissolved in, okay? In solutions, the solute cannot easily be filtered or separated out. The book says it just cannot be filtered or separated out. There are some methods to do that in many cases, though. And so here's my little caveat on the book, except through methods like evaporation, distillation, and chromatography. So in evaporation and distillation, we're talking about phase changes. And so that's like one of the only ways that we can filter out the solute away from the solvent in solutions is by taking advantage of the properties of the chemicals where one will have a phase change at a certain temperature and the other will not. So for example, if we have a solution of salt water, if we boil that salt water, eventually all of the water will evaporate out and the salt will still be left. And that is a way to separate out the salt. Now, if we just try to strain that salt water through filter paper, the salt's just going to go right through the filter paper along with the water. Okay. Another possible way is chromatography. So within solutions, there are three types of solutions that you need to know, okay? And they are based on what the phases are of the solvents, the solutes that are in them. So we have solid and liquid solutions, okay? And so great example of that is salt water, right? The salt is actually solid in that solution, and we can evaporate out the liquid even without boiling, right? If it sits long enough, that liquid will evaporate, and you're left with the salt. There's then powdered drink mix would be another example of a solid and liquid solution. In solutions, the solutes, they're not going to settle, right? They are part and parcel of the solution. And then we have liquid in liquid solutions, okay? And so these are things like extracts, right? So a vanilla extract, it is actually a liquid that is, it's been distilled somewhat, but the particles that are in there, the solutes, is a liquid. Vinegar that you buy in the store is not 100% acetic acid. It is some percentage of it. So most of the vinegar that you buy just in the grocery store is, I think 5% is what is most common in the grocery store. You can possibly buy more concentrated versions that are for cleaning, and you might get these at like Lowe's or something, because they're much more corrosive, but still only 30% acetic acid, right? But acetic acid is a liquid. And so if you were to get 100% acetic acid from some scientific supply company, it would come as a liquid. But these are diluted for use at home. Right? Oils are liquid and liquid solutions. And why is that? It's all oil, right? Well, different kinds of oil, right? There's different fatty acids that are a part of this vegetable oil, right? You may also have oils that are combinations of oils. So vegetable oil, most often vegetable oil is just soybean oil, but because it just is called vegetable oil, if you look on the back of the ingredient, there might be some vegetable oils that are a combination of different vegetable oils, and they're going to stay together in solution. They are a solution, but it's liquid in liquid. Okay, the third type of solution that you need to know are gas in liquid solutions. All right, so basically we just need to remember the three phases, right? Solid, liquid, and gas in liquid solutions. Okay, and so gas and liquid solutions are things like club soda. So club soda is just, it's going to be water with carbon dioxide in it. Now, soda like Coke is actually a combination. It is a gas and liquid solution, but it is also a solid and liquid solution. It is also a liquid and liquid solution. So in Coca-Cola, the solids, an example of the solids, there's many, would be sugar, right? So the sugar went in as a solid and is stirred in, and that becomes part of the solution. Liquid, well, there's high fructose corn syrup, right? And that is a liquid. Uh, Acids that are added to cola. So these are all part of the example of liquid in liquid solutions in Coca-Cola. And then, of course, for gas in liquid solution, we have the carbon dioxide that is in the cola. So it's a combination example of all three. If you want to be tricky and I ask for examples, give me Coca-Cola on all of them, but you'll have to explain it. Okay. All right. So what affects how soluble the solutes are in the solvent? And this should be a lot of review for those of you who have had chemistry. If you haven't, it's not too difficult to know. But so temperature, as temperature increases, our solubility increases. You think about if you've ever made sweet tea, that sugar goes into solution a lot more easily when the tea is warm versus if it's ice cold. Or if you add honey to tea, it's going to go into solution a lot more easily when it's warm than when it is ice cold. So as the temperature increases, the amount of solid solute that the solvent will hold also increases. Okay. Now, that's true for solids, okay? But if we're talking about a gas in liquid solution, we actually have a reverse effect, okay? So as the temperature increases, the amount of gaseous solute the solvent will hold decreases, okay? And that's just because of the particles, not particles, the attributes of gases versus solids and liquids, right? So as temperature increases, things are moving more rapidly in a solution, right? We always have particles moving and things move more rapidly. That is why solid solutes will increase in solubility when the temperature increases, because they're able to loosely bind to the solvent more quickly because of everything moving more rapidly. Like that, the solute can grab, or the solvent can grab some of that solute more easily. But with gas, well, when gas is moving more quickly, it is going to hit the top of that liquid more quickly, right? And the ideal place for that gas is not in that liquid, okay? It wants to come out because it is less dense. So when that gas hits the top of that liquid, it's going to come out of solution, okay? And so the easiest way to think of this is soda, all right? If you have soda and you got it at a restaurant and it was, in ice water and it's nice and fizzy and, burns going down your throat, and then you leave it in your car for even a few hours in the heat. When you come back, it is pretty much flat by that point. If you leave it a day, it's completely flat. And that is because with that heat especially, that accelerates how fast that gas is going to come out of solution. Now that gas is going to come out of solution even if on a cold day if you don't have it in that bottle, because the pressure of the bottle also holds the gas in there, which is a little bit separate thing. But the hotter it is, the faster that's going to happen. Okay, particle size also affects solubility. And so the greater the surface area, the faster that solute will dissolve. So if we think about having a sugar cube versus individual sugar granules, how the dissolving happens is that solvent kind of grabs onto and loosely binds with that sugar, and it's more of like an attractive force. But if the sugar is in a cube, there are fewer. This cube is not the well, yeah. There's fewer areas on there's less area on the cube for the solvent to attract and dissolve the sugar, right? Versus if it is granules, there's a lot more surface area for it to do that. And so it's going to be able to work more quickly dissolving the solute when there's more surface area, which means that we have smaller particle sizes, okay? The next factor that affects solubility is concentration. Okay, and so concentration, simply defined, you have the parts of the solute divided by the parts of the solution, and that equals the concentration. You can use different units for that. So we're not going to go into units or having you calculate any concentrations, because I kind of determined a while ago that I wasn't making calculation a big part of this course. But parts of solute divided by parts of the solution equals the concentration. Okay. Once the solution holds all the solute that will dissolve into the solvent, it is called saturated. So at that point, no more solute can be dissolved into that solvent. Okay, and that is called saturation. Now, saturation is related to temperature, so the higher the temperature, the more that the solvent can hold the solute. So the more solute the solvent can hold, the higher the temperature is. Okay, so example of this, back when we did sugar, and I made what was called a supersaturated solution of sugar. I boiled sugar and water, and I was able to have more sugar get dissolved into that water than if the water had remained at room temperature. And the nice thing about sugar solutions is that they can become what's called supersaturated, which means that it holds a higher concentration of the solute than would normally be possible at that temperature. Okay, so how that works is that adding heat gives the energy needed to break hydrogen bonds between sugar molecules, and then that heated solution can hold more solute. And so this supersaturation is how candies are made, because sugar is very easy to get supersaturated with heat. The fourth factor that affects solubility is the pH. And by pH, I'm also talking about charges. Okay. So singly charged ions tend to be more soluble than ions with 2 or more charges. So examples of some singly charged ions are sodium and chloride. Right? They each have a charge of +1 or -1. They are going to be more soluble than ions with 2 or more charges, such as calcium ions or magnesium ions. The other thing about ions is that smaller ions are more soluble than larger ions. Okay, so this is roughly comparative sizes of 3 ions. Okay, this is the ammonium ion, and it is actually smaller than a chloride ion, because nitrogen is smaller than chloride, and hydrogen is much smaller. These blue numbers here are the atomic radii of these. Okay. So ammonium, this ammonium ion is going to be more soluble than chloride, and chloride is going to be more soluble than iodide. Okay, and this is all just based on the size of that ion. So the smaller the ion is, the more soluble it is. Just similar to our particle size rule, right? It just applies to ions as well. Okay, So more factors affecting solubility are agitation. So we know that stirring will speed how fast something dissolves until that saturation point is reached. Once the saturation point is reached, then you're done. But this is one that's pretty obvious, right? You add sugar to your tea, stir it, and it's going to dissolve into the solution much more quickly than if you just let it sit there. Eventually it would dissolve into your tea if it just sits there, but it's going to take a lot longer. And vapor pressure. The pressure at which gases escape from and dissolve into a liquid at the same rate. That is what vapor pressure is defined as. And so this pertains to gases only, right? Because this definition includes gases. So this is only affecting this solubility of gases. And so this is why when the seal on your carbonated beverage is broken, those gases escape, because you have lost that pressure that was holding the gas into the liquid. Okay. The pressure over the liquid when that seal is broken is much less than the pressure in the liquid, and so that liquid is just going to push that gas out. This is basically how that works. When that seal is still there, it's pressurized, right? And so that pressure over the liquid is still high. Okay, so those were all of the factors affecting solubility. You have vapor pressure, agitation, pH, concentration, particle size, and temperature. There's 6 of them. Okay, applications in the beverage industry. And the reason we focus on the beverage industry is that solutions are consumed the largest amount in beverages. So, soft drinks. Our solvent is water. Our solutes, we have sweeteners, flavoring, coloring agents, acids, carbon dioxide. And what does each of these things do? Carbon dioxide gives the fizz and the acidity to cola. Carbon dioxide is acidic, so it contributes to that acidity. Citric acid and phosphoric acid also contribute to acidity, and these, so here's our gas. Hold on. Sorry, kid. Okay, so carbon dioxide is our gas in liquid, right? Citric acid and phosphoric acid would be our liquid in liquids. Although citric acid you can get in a granular form too, so that might be a solid and liquid. Sodium benzoate is preservative. So there is a solid and liquid. And so our solvent, our water, must be high quality so that we don't get interactions that we didn't plan on. Because if you have lots of minerals in the water, then it might interact more with the acids or the preservatives or the sweeteners. And so it's just kind of an aside. The water is highly controlled in the beverage industry, not just soft drinks, but the entire beverage industry, because otherwise you can have completely different products from one day to another, even because like you think about how cities treat their water, like sometimes they add all this treatment at one time, and so the water tastes different from day to day, and that's because there's different things in there. But also, especially like the bigger beverage companies, they have multiple bottling plants in different places all over the country. And so you want a Coke from Texas to taste the same as a Coke from New York. And that consistency is important. Okay. Other beverage industry applications, coffee and tea, right? So coffee and tea are affected by the type of coffee bean or tea leaf. So typically that's going to be something that is marketed as, right? the drying process that is used, the roasting times. So how long are you roasting these beans? And that's going to affect the flavor compounds. The particle sizes, of course, right? So, you know, if you have a finely ground coffee, that's going to brew very differently than a coarsely ground coffee, and that's because of our attributes of solubility, where particle size affects how soluble the solvent is. Any flavoring agents that you use. Brewing time. So, you know, how long do you brew the coffee or steep your tea is going to affect the flavor. If you have a finely ground coffee, you can brew it for a much shorter time, but if you have a coarsely ground coffee, you might be brewing it for a longer time or differently, right? There's different brewing temperatures that result in different end results. And that brewing temperature, remember, affects the solubility of those compounds in the coffee and tea that give us what ultimately is what we drink. Okay, so the second type of mixture is colloidal dispersion. So everything that we've covered through so far is the solutions. And now let's talk about colloidal dispersions. So in these, the particles are bigger, right? They are generally going to be microscopic. You're not going to be able to see them with the naked eye, but they are evenly distributed still in the other substances. So examples of colloidal dispersions are emulsions, foams, and gels. Okay? Emulsions, foams, and gels are our biggest examples of colloidal dispersions. There are some others that we'll talk about, but these are three. I don't want to say categories because not everything that's a colloidal dispersion fits in one of these categories, but they kind of are, right? There are some categories that fit into the classification of colloidal dispersions. Okay, so what does colloidal dispersion mean? Well, colloids are the dispersed phase in a colloidal dispersion, right? So what colloids are is they're macromolecules, so they are things like protein and fat or clumps of smaller molecules. So starches, uh, proteins, big clumps of fat, okay? These are all the colloids. And then dispersion, it just means that those colloids are dispersed. And so they are the dispersed phase. So, like we've said, these are going to be larger than solutes, up to 1,000 times. And they are not going to dissolve, okay? So they are not going to be forming the same type of interactions with the water, and therefore they will not impact boiling or freezing points. Okay, so we've talked before about salt, how salt affects boiling and freezing points, how sugar affects boiling and freezing points. Colloids do not affect the boiling or freezing points of their mixture. Okay, so some common examples of colloidal dispersions are jellies, mayonnaise, butter, gelatin. Hold on a second. Okay, the guest star is gone. Our cameo. Okay, so how colloids are dispersed. What makes a colloidal dispersion? Okay, so the continuous phase in the colloidal dispersion or a solution is going to be moving, okay? But in the case of a colloidal dispersion, that continuous phase is going to be moving faster than the colloids, and that keeps them dispersed. It kind of keeps them from settling or rising to the top. Okay. Electrical charge can also play a factor. Often these colloids have an electrical charge and they're going to repel each other, and that is going to keep them separated and not precipitating together. Once they're repelled, the water kind of forms a cushion around them, and so this is just a way that in many cases the colloids remain dispersed and not again settling down to the bottom or rising to the top or converging all together. Okay. And density. So in many cases, this keeps everything dispersed, but if the colloids are much denser than the continuous phase, they may settle. And if they are much less dense than the continuous phase, they may float to the top. Sometimes these properties can overcome the density, but if the density is too much greater or less than the continuous phase, then you can have settling or floating. So another example of a colloidal dispersion is homogenized milk. So this one is this is an example of one that doesn't really fit in those three categories of emulsion. Well, it is, I guess it is an emulsion. Take that back. It does fit in an emulsion. Okay. So homogenized milk. So homogenized milk it's both a solution and a colloidal dispersion. Okay. There are parts of it that act like a solution and the parts of it that act like a colloidal dispersion. So in the solution part, our continuous phase is water. Okay. But dispersed throughout that are lactose and mineral salts like calcium. Okay. So these are in solution. This solution then acts as its own continuous phase within the colloidal dispersion. Okay, so the continuous phase of this colloidal dispersion of homogenized milk is this solution of water, lactose, and mineral salts. Okay, and then the dispersed phase colloids are going to be the proteins and the fat that are in the milk. And they will form an emulsion where the protein surrounds the small fat globule and allows it to have interaction with the water and not completely rise to the top and not coalesce and coagulate together. Okay. So before you homogenize it, you have these big fat globules, and there's no way they're going to get completely covered with the protein. And because they might get covered a little bit and then it'll escape. Okay. And so the fat ends up floating up to the top. But when you homogenize it, those fat globules are smaller. The protein is able to coat it, and the interactions with the water and the reduced size lead to it just staying dispersed within the solution of water, lactose, and mineral salts and not float to the top. So these definitions of our different types of mixtures, they're not purely discrete, right? You're going to have like mixtures of mixtures, okay? Okay, so emulsions. We've talked a lot about emulsions in this class, so you should be pretty familiar with what an emulsion is by this point, a mixture of two immiscible liquids. And there are there is such a thing though as a temporary emulsion. And because the term emulsion, a mixture of two immiscible liquids, does not mean that they have to stay mixed, okay? And so a temporary emulsion would be an unstable mixture of two immiscible liquids, or we could call this an unstable emulsion, okay? So example of that would be if we just have oil and vinegar and put them together for a salad dressing, we shake them up, right? And they're mixed, but very, very quickly they're going to separate again. And that is a temporary emulsion or an unstable emulsion. Now, if we add an emulsifier, which again, y'all should know this pretty well by now, is our molecule that has a polar and a nonpolar end. And so that's going to stabilize that emulsion, and you can have it interacts with the water and the oil and keeps everything stable. So examples, again, familiar words, right? Lecithin, our monoglycerides and diglycerides are examples of emulsifiers. So there's two types of emulsions. I don't remember whether we've covered this before. If we have, great, more review. Oil and water emulsions. Okay, so this means that the continuous phase of the emulsion is water. Okay. So oil in water solution would be things like salad dressing, mayonnaise, ice cream, cake batter. And then, and so we have more water actually in this emulsion than we have oil. Okay. Other type of emulsion is water and oil emulsion. So examples here, butter and margarine are the best examples, right? These are mostly oil, and there are small droplets of water that are dispersed throughout these emulsions. Okay, so water and oil emulsion, the continuous, let's do it opposite. Oil and water emulsion, the continuous phase is water, and the dispersed phase is oil. Water and oil, continuous phase is oil, dispersed phase is water. Okay, so foams are another type of colloidal dispersion. And so in foams, we're going to have a dispersion of gas or air bubbles in a liquid. Okay. So we have unstable foams. This would be like the froth on a carbonated beverage, on a cola. Okay. That foam is going to disintegrate eventually and not be a foam anymore, right? It will settle. Versus stable foams are things like whipped topping, so whipped cream, and meringue, where we have that egg white that we've made into a foam. So what are the requirements for a foam to be stable? Well, the liquid must be viscous enough. It must be thick enough to hold that air. Okay, so we think about a soda, that liquid is not thick, right? And that is why that air just eventually comes out of the foam. It needs to contain a stabilizer that will stretch to form a film around the bubbles. And so stable foams are actually emulsions of air that are in oil or fat or protein globules. Okay, that stabilizer is the oil or the fat or the protein, one of the two. And the surface tension of that film should be less than that of water. And the liquid should have a low vapor pressure. The liquid that the foam is made of should not be able to evaporate easily, which is another reason that soda foams are not stable. Okay, so factors that affect foam stability. So one thing before I even get started on this, we're going to focus a lot on whipped cream and egg foams and meringues, okay? And you're going to notice that in a lot of these factors, it's like opposite. And that's because those foams are made of two different things, all right? With whipped cream, we are taking advantage of the properties of a fat. Okay, so it is let me back up. Oh, maybe not. Sorry, it is a air in fat emulsion. Okay, uh, with the egg foams, egg white foams, we're an emulsion of air and protein, and so that's going to flip some of the factors that affect the foams, and it'll affect them differently. Okay, so just be watching out for that. Uh, Not everything is opposite, but a lot of them are. Okay, so factors that affect foam stability. Temperature. When we are making whipped cream, chilled temperatures are better because it makes the fat thicker. So that what makes a stable foam a viscosity. That fat's thicker. It holds that air better because it's thicker. Okay. With eggs, a moderate temperature, so slightly warm temperature, makes it easier for those proteins to denature. Well, when proteins denature, they're thicker, okay? And so it's temperature being used differently, right? In the cream, we want cold because it makes the fat thicker. And with the eggs, we want warm because it makes the protein thicker, okay? And so it forms that film better when it's denatured and thicker. Fat. Okay, so obviously cream is high in fat, right? And that high fat is what gives the cream its viscosity and the thickness that holds the air better trapped in the foam. Okay, in eggs, opposite, right? The fat in eggs is going to interfere with the foaming ability of the protein. So in cream, you want high fat. Higher the fat, the better the viscosity is going to be. In fat, even a tiny, or sorry, in eggs, even a tiny amount of fat is going to interfere with the foaming ability of the eggs. Okay, then solutes. Okay, so what other things are part of the foam? This is one where it's the same for cream or eggs. Sugar will increase the foam stability by stabilizing the water that is in the foam. Okay, acidity. So with whipping cream, you want the cream to be as fresh as possible, and that is because lactic acid bacteria will grow, consume that lactose, produce lactic acid, and so that lower pH can disrupt the casein that is part of the emulsion. Okay, so protein does play a factor in in whipping cream, less of a factor than fat, but the casein is important, and you don't want a low pH that disrupts the protein. Okay. The same is true for eggs. Okay, so here's another one where they are the same. Okay, fresher eggs are better, and stop, back up. I just said that wrong. Okay, the same is true for eggs in the fact that fresher is better, but for the opposite reason, and that's because as we've talked about before, when eggs age, that pH increases. Okay, so When cream ages, the pH decreases, and that's bad. When eggs age, the pH increases, and that is bad. Okay, so you want fresh for both of them, but for opposite reasons. The pH will increase in eggs to a point where it causes issues. Now, if we added acid to the eggs, it actually can be a good thing as long as you're not adding too much acid. And we actually, in fact, do purposely add cream of tartar to lower the pH and increase the stability of the protein. Okay, so I said this wasn't opposite. It kind of still is. Okay, like with whipping cream, we're very careful to not add acid. With eggs, sometimes we purposely add acid to increase stability. Okay, so that was it for foams, and I'm not going to talk about gels, which was the third one for colloidal dispersions. And we're going to go into suspensions, which was the third type of mixture that we're covering. And this is the last slide. Okay, so mixtures are mixtures of undissolved particles, so they're not part of solutions, that are suspended in a liquid in some way. Okay. The viscosity of this liquid is the only thing that keeps these particles from sinking. Suspensions, these particles, you can see them with your eyes. Okay. They are not microscopic. So examples, unhomogenized milk. Okay. So yes, at the beginning, you may not be able to see that those flat globules, but within a matter of time, you'll see those flat globules rise to the top, okay, because they will coalesce up at the top. And so therefore, it is a suspension. Hot chocolate is also a suspension. Now, you don't necessarily see the individual particles that are in that suspension, but leave it long enough, those particles do eventually sink, and you can see like they're undissolved, and they are individual particles that you can see with your naked eye. Italian dressings would be one. So all of the spices and things that are suspended in an Italian dressing make up that suspension. Fruit juice with pulp. Okay, the pulp is suspended in that liquid. Fruit that's in gelatin. Ice cream with inclusions. So inclusions are anything that has been added to the ice cream that's suspended in it. That's not part of a colloidal dispersion or solution in the ice cream, but actual like pieces that have been suspended. So, the fudge or nuts or candy, cookie dough, right? Cookies, all right? All of those are inclusions in ice cream. And so ice cream is a ice cream that has any other like inclusions added would be an example of a suspension. Now, like vanilla ice cream, that would not be an example of a suspension. But as soon as you start adding things to it. So that is it. Oh, wait, hold on. Batters and doughs with inclusions. So chocolate chip cookies, right? Those are a suspension before you cook them. Or brownies, it's a liquid, right? You add some nuts, it's still a liquid, but it has those inclusions, so it's a suspension, that dough and the nuts. Okay, so that is it for this chapter. Yay, last lecture, last chapter, and I hope everybody does well on the last exam. There is a fun surprise in that last exam, and I hope everybody gets lots of points. So I have enjoyed teaching this class with you all. I hope you have enjoyed it as well and gotten a lot out of it and are all well-informed consumers now. So thank you.